That's approximately 0.46. So plus or minus 0.46. We can put that on the number line as our critical numbers, negative 0.46 and 0.46. We've got our first derivative. If we test the easiest one, of course, is to test what's in between, which is 0. And here's our derivative, so 0 would give us negative values. Something to the right of 1 would give us a positive value, and a negative 1 would give us a positive value also. So that means we have a max at negative 0.46, and you can plug it in to get the y, and we have a min at positive 0.46. Now we take the second derivative. A little tougher because we have to take the 2/3 times the 5/3, which gives us 10/9, and then decrease the 2/3 by 1, which would be negative 1/3, and then the derivative of 1 is just 0. So we set that equal to 0, and the only way that this could equal 0 is if x is 0. So we put that on our number line, and we test. If we test a 1 back in the second derivative, that's going to be a positive. And if we test a negative 1 to the left of 0, cube root of negative 1 is negative 1, and then negative 1 to the negative 1 power is the same as negative 1 over 1. So that would be a negative value. So that means it's concave up from 0 to infinity. It's concave down from negative infinity to 0. And the point of inflection is at 0. We plug that in the original, and we get 0. So that gives us everything we needed for number 49. Now we need to move on to the L'Hopital's rule that we did today, and look at the homework from that. So on page 229, you had number 1, and here it says, use L'Hopital's rule to evaluate the limit or state that L'Hopital's rule does not apply. Remember, you have to have the indeterminate form, 0 over 0 or infinity over infinity, to be able to use L'Hopital's rule. So the first one is the limit as x approaches 3 of 2x squared minus 5x minus 3 over x minus 4. Well, we cannot use L'Hopital's rule here because when we plug the 3 in the denominator, that's the easiest place to plug it in, we don't get a 0. We can figure out the limit, but L'Hopital's rule does not apply. So moving on to number 6. So the first thing we need to do is to plug the 3 in. When we plug it in the numerator, we do get 0. And when we plug it in the denominator, we also get 0. Which means that we can use L'Hopital's rule. And we would take the derivative of the numerator over the derivative of the denominator. And then we try to plug the 3 in. So when we plug the 3 in the denominator, 3 squared is 9, times 3 is 27, minus 7 is 20. And when we plug the 3 in here, 3 plus 1 is 4. The square root of 4 is 2. 2 to the negative 1 is 1/2, times 1/2 is 1/4. So that ends up being 1 over 80. So we can evaluate with L'Hopital's rule on that one. Number 11 was the limit as x approaches infinity of 9x plus 4 over 3 minus 2x. Okay, and what happens here, if we try to plug the infinity in, you can't really plug infinity in, but you can talk about what happens as x gets larger and larger and larger. Okay? And so this numerator would get larger, And the denominator, this is going to be 3 minus 2 times a number that gets larger and larger. So that one's going to go to probably to negative infinity. So we can use L'Hopital's. So the derivative of the numerator is 9. The derivative of the denominator is negative 2. So this limit is just negative 9/2, or negative 4.5. The limit of a constant is a constant. This you should also recognize is actually the horizontal asymptote of this function, 9x plus 4 over 3 minus 2x. Moving right along, number 17 is the limit as x approaches 1 of square root of 8 plus x minus 3x to the 1/3 over x squared minus 3x plus 2. I believe that's a square. Yeah. So if we put a 1 in there, we are going to get 3 minus 3. And we put a 1 in the denominator, we get 0 also. So we would use L'Hopital's. And so the derivative of the numerator would be 1/2 times 8 plus x to the negative 1/2 minus 1/3 times 3 is 1, x to the negative 2/3 over 2x minus 3. So if we put the 1 in there this time, in the numerator, we'll have 8 plus 1 is 9, square root of 9 is 3, 3 to the negative 1 is 1/3, times 1/2 is 1/6, and then the cube root of 1, well, 1 to anything is going to be 1, so that's going to be minus 1. In the denominator, 2 times 1 is 2, minus 3 is negative 1. So we'll have negative 5/6 over negative 1, which is 5/6. So that would be evaluating the limit using L'Hopital's for number 17. Number 21. Limit as x approaches negative infinity of 7x squared plus 4x over 9 minus 3x squared. Again, you're going to get L'Hopital's rule. The requirements are met. So we just take the derivative of the numerator, which is 14x plus 4, over the derivative of the denominator, which is negative 6x. But we notice that we get L'Hopital's rule requirements again. So we have to use L'Hopital's rule again. Derivative of the numerator is 14. Derivative of the denominator is negative 6. So your answer is negative 7 over 3 for that one. So you had to use L'Hopital's rule twice on that one. 25. Limit as x goes to 0 of sine of 2x over the sine of 7x. L'Hopital's applies because you have 0 over 0. So the derivative of the numerator is cosine 2x times 2. Derivative of the denominator is cosine 7x times 7. So when we put the 0 in at this point, cosine of 0 is 1. 1 times 2 is 2. Cosine of 0 is 1. 1 times 7 is 7. So this limit is 2/7. Number 31. The limit as x goes to 0 of cosine of x plus pi over 2 over sine of x. 0 over 0. So we'll take the derivative of the numerator and the derivative of the denominator. So the derivative of cosine would be negative sine of that same thing, x plus pi over 2. And then the derivative of the sine is the cosine. So now we should be good, because if we put the 0 in there, the sine of pi over 2 is 1, so that's negative 1. Cosine of 0 is 1, so this limit is negative 1. Number 39. Limit as x goes to 0 of e to the x minus 1 over sine x. 0 over 0, use L'Hopital's. Derivative of the numerator is e to the x. The derivative of the denominator is cosine x. E to the 0 is 1. Cosine of 0 is 1. So this limit is 1. That one was kind of easy. All right. So we're going to 43, the last one. The limit as x goes to 0 from the right of, actually it's t, but I'll put an x in there. Sine of x times the natural log of x. Now this is like the one we discussed in class where you don't have a quotient, so you need to write it so that you do have a quotient. So you can write the numerator, if you want, as the natural log of x, and the denominator is 1 over the sine of x, and that would be writing it as a quotient. And now if we take the derivative of the numerator, it's 1 over x. The derivative of the denominator that's 1 over sine x, which is the same thing as cosecant x. So it would be negative cosecant cotangent, or you can use the quotient rule there if you want to. That would have to be the sine of x times 0 minus 1 times the derivative of the sine of x over the sine of x squared. So let's just write it as negative cosecant x cotangent x. Okay. So now, if you look at this, 1 over x over the negative cosecant x cotangent x, we still have an issue because we're going to have infinity over infinity. So you would have to go again. Okay. So it looks like with this one, we're going to have to go more than once, and this might not be the best way. We might could do a 1 over natural log of x here instead of a 1 over sine x, because as we look, 1 over x, as we approach 0 from the right, is going to be going to a positive infinity. And then this one, negative cosecant x cotangent x, is going to go to, you'd have to graph that one to see what it's going to approach as x approaches positive infinity. So I think you'd have to go one more time. I think I'm out of space on this one. But you'd have to go again because this is infinity. And then you'd have to graph this. So let me go on to the lesson, and we'll pick up with that one. Since it is kind of more complicated, we'll pick up with that one